Good day and welcome to part one of our discussion on integration by parts. The next major topic of interest in Calculus 2 is integration. We are going to spend this entire chapter focusing in on various different techniques of integration. And today we're going to start with a technique referred to as integration by parts. And to get us thinking about integration by parts, I want to start off with a motivating example. Can we integrate x e to the x? And at face value, this is a fairly challenging problem. When it comes to integration, as a student leaving Calc 1 or at this current point we are in Calc 2, we essentially have two main approaches. Use either a direct comparison to our table of common indefinite integrals or get there with algebraic manipulation. If that doesn't work, we use a substitution. Now we're going to add to our list. Now, the observation I'm going to make to get started is differentiation in general is much more straightforward than integration. So we could differentiate this function with no problem whatsoever. So let's do that just for fun. When I differentiate x e to the x, I do so with the product rule. We take the derivative of the first times the second plus the first times the derivative for the second. And in this case, note something interesting happens. This function we would like to integrate, x e to the x, it comes up when we differentiate x e to the x. So let me go ahead and just directly rewrite this quantity by isolating the x e to the x. If I wanted to isolate x e to the x and leave it on a side all by itself, the other side of the equation would contain that derivative we started with, and I would also have to subtract e to the x from both sides. Now that we've made this kind of side observation, let's go ahead and integrate x e to the x. And I'm going to do so by simply just adding an integral in front of each of the terms that we have above. So this would be the integral of the derivative of x e to the x minus the integral of e to the x. And note, an integral of a derivative cancels each other off, and we're left with x e to the x. And we know an antiderivative of e to the x. It's simply itself, plus c. And this example works out extremely nicely, and it's kind of a special case. But the observation we can take away from this is we've somehow undone the product rule of differentiation. And remember this idea, every rule of differentiation should have a corresponding rule of anti-differentiation. And in general, integration by parts is going to undo the product rule of differentiation. So let me think about this now a bit more generally. If we have two functions multiplied together and we differentiate them, the product rule tells us we have f times g prime plus f prime g. And we can go ahead and integrate this just term by term. So the indefinite integral of fg prime, and we know what's going to happen when we integrate the derivative. Then we would have the integral of f of x g prime of x plus the integral of f prime x g of x. So note in the first term, the indefinite integral of the derivative cancel each other, and that term simply becomes f times g. And what I'm going to do, and it's maybe not obvious why at this point, is I'm going to go ahead and isolate this first term on the right. If I solve for the integral of fg prime, this would be equal to the fg that we have left over on the left-hand side above, but then we need to subtract this f prime g term to really isolate as necessary. And this is the formula which gives us integration by parts. I prefer to write it in a more, what I consider, convenient form. So I will almost always abbreviate integration by parts with IBP. And I'm going to use differentials much like we would with a substitution. If we let u be equal to f of x and v equal g of x, then du would be f prime x dx, and dv is g prime x dx. And with that observation in mind, the line above can be rewritten as the integral of u dv is equal to uv minus the integral of v du. And this is the formula I will almost always use and think about for integration by parts. Let's go ahead and see if we can apply integration by parts to our motivating example. When we are using integration by parts, we always need to start off with a choice. And that choice is what's going to play the role of u and what's going to play the role of dv. So we're starting with this integral on the left, and then we apply integration by parts to get what is on the right. So when we look at the integral of x e to the x, we very clearly see two functions. There's an x and an e to the x. I'm going to go ahead and just make a choice, and we'll see what happens with it. I'm going to let u be equal to x and dv be the e to the x. So we have our u and our du. In order to apply integration by parts, as we see above, we need to find du and v. We get du, as we typically do, dx, and to get v, we need to anti-differentiate this dv, and it ends up being e to the x. And integration by parts tells us the following. It tells us u times v, which is x e to the x, minus v du. So minus the integral of e to the x. And immediately we are done. Now, an observation I want to make is I will almost always organize my work in this fashion, where I put the integration by parts to the side with the u and the dv, but I always organize it as u du v dv, because then it helps me very efficiently remember the integration by parts formula. Going back to our observation that we need to make a choice for u and dv to start this problem, you might be wondering, does it matter if we switch around the role or the choice that we make for u and dv? Well, let's see what happens. If I want to evaluate this integral, x e to the x, and we make the opposite choice. So let's let u be e to the x and dv be the x dx. And note, when you multiply together the u and the dv, you should get this entire integrand. So u can be differentiated to find du, and dv can be anti-differentiated to find v. Integration by parts tells us uv minus the integral of v du. So that would be 1/2 x squared e to the x minus the integral of v du. 1/2 x squared e to the x. And note what has happened here. The resulting integral that we have to evaluate has gotten more complicated. Whereas in the previous example, that resulting integral was simpler and easier to evaluate. So in this case, more complicated is not good. So the choice that you pick for the u and the dv absolutely makes a difference. In general, I would say integration by parts can be applied when we are integrating a product. It undoes the product rule of differentiation. But remember, it does not immediately solve the integral for us. What it does is it rewrites it in terms of what is hopefully a simpler or easier to evaluate integral. And some intuition we'll come back to multiple times is when you're making your choice for u and dv, at a minimum, dv needs to be something you can anti-differentiate to find v. Ideally, the u becomes simpler when we differentiate it. So above, the x became a 1. It became simpler. Let's finish the first part of our discussion by looking at an example that shows a nice way to apply integration by parts when it may not appear possible at first. So our intuition, this is not a function we know how to integrate. And what I mean by that is we do not have a common formula that we can use. It does not appear as though substitution can even be applied. And that really only leaves us with one possible choice: integration by parts. And as we continue on our discussion of integration techniques, in the background there's always going to be the thought process of why do we apply a certain technique. When we are in this section talking about integration by parts, you probably have a very good suspicion that's a technique we're going to use. But when we get to the exam and you have a list of integrals to evaluate, your first and sometimes most difficult choice is what method of integration should you use. So in this case, we're going to use integration by parts. And remember, with integration by parts, we need to decide what's going to play the role of u and what is going to play the role of dv. And one way to think about this single function arctangent is 1 multiplied by arctangent. So implicitly, there's always the 1 kind of hiding there in plain sight. And I want you to take a moment, pause the video, and write down on your paper, what is your choice for u, what is your choice for dv? And think carefully about it. So in this case, I'm going to say there is absolutely a good choice to be made. And there's also a very bad choice to make. Let me first write down the choice that's maybe not the best one. If I chose dv to be arctangent, then to find v, you would need to anti-differentiate arctangent. But if I knew how to anti-differentiate arctangent, I would not be using integration by parts. So whatever choice we make for our dv must be something we can integrate. So we're going to let 1 be the dv and arctangent play the role of u. Now we're good to go, at least from a procedural perspective. Du is 1 over 1 plus x squared, and the antiderivative of 1 is simply x. So integration by parts tells us uv minus the integral of v du. So we have x arctangent minus the integral of v du. So x over 1 plus x squared. And as long as we can evaluate this resulting integral, we're good to go. And at this point, I would like you to pause your video and give yourself maybe 60, 90 seconds. This should be a quick integral to evaluate, and finish up this problem. And hopefully at this point you've finished up the problem, and if not, pause the video and really do that. So the x arctangent of x comes down for the ride. And when it comes to evaluating this integral, it's an ideal scenario to use a substitution. So note, a given problem might require multiple techniques of integration, i.e. an integration by parts, and then a substitution. We would let our u be 1 plus x squared, so that du is 2x dx. Or stated differently, 1/2 du is x dx. Now note, I'm using u to play two different roles in the same problem. As long as it's clear from your work at each step what role u is playing, that's perfectly fine. And here using different colors, I guess, makes it extremely easy to see that. But if you prefer, instead of saying a u substitution, you could simply call it a w substitution. Either approach would be okay with me. So the x dx becomes 1/2 dw, and we are subtracting away 1/2 the integral of 1 over w. That resulting integral is one that we can evaluate quickly and efficiently. We have the natural log of the absolute value of w. And our last step is to resubstitute and get back in terms of that original variable. And as I usually do, let me just take a moment and mention that the notation is very important. There's a tendency to do things like maybe forget equal signs, or after the first step not write these x arctangent of x terms down, but we write each and every part at every single step, and we use proper mathematical notations, integral symbols, dx's, and when we have these side computations, we put them to the side so that we can organize our work in a single vertical column. And this finishes up our current discussion, but notice the next example on the note sheet. This is a great opportunity for you to hopefully quickly practice integration by parts. So before going on to the next video, give yourself just a couple minutes and evaluate that integral, which is where we will pick up next. So stay tuned and take care.